everyone. My name is Tianzhima. Today, I'd like to present our paper titled CiD4HMOS, a solution to HarmonyOS Compatibility issues. The contributors to this work are from Nanjing University of Aeronautics and Astronautics, Monash University, and Beihang University. This presentation comprises 5 sections: background and motivation, detailed approach, study design, study results, and conclusion. HarmonyOS was launched by Huawei in August 2019 as an operating system. By September 2020, they announced its deployment for mobile phones. Up until now, Huawei has rolled out 3 major HarmonyOS versions, along with 8 API versions. The release dates and the system versions for API versions 1 to 3 have become unknown. Thus, our work is centered on API version 4 and subsequent ones. Table 1 displays correlation between the API versions and HarmonyOS versions, detailing their respective release dates. As a brand new operating system, HarmonyOS SDK faces similar API compatibility issues as other SDKs or Android. These challenges primarily arise from addition, removal, and depletion of APIs during version updates. Existing solutions for API compatibility issues have mainly catered to Android, leaving a gap in effective solution for HarmonyOS. Therefore, our research primarily addresses these issues in this domain. Before diving into our approach, let's first understand the reasons behind API compatibility issues. These issues are primarily of 2 types: backward and forward compatibility issues. Figure 3 clearly clarifies the principle behind these issues. In simple terms, a backward compatibility issue arises when an app runs on a system API version lower than its actual compatible version. Conversely, a forward compatibility issue occurs when an app operates on a system API version higher than the version it's truly compatible with. Figure 4 illustrates the operational flow of CiD4HMOS. CiD4HMOS is designed to identify all API compatibility issues within the provided applications. Our concept draws inspiration from the CiD, introduced by Lilly and his colleagues in 2018. Firstly, we introduced HarmonyOS API lifecycle modeling. In this section, we extract APIs from official HarmonyOS SDK and create a comprehensive lifecycle model for all HarmonyOS APIs. HALM is structured around 2 pivotal stages: API extraction and API lifecycle modeling. Through this phase, we have developed a lifecycle model that can pinpoint the exact addition and removal dates of any API within HarmonyOS SDK. The second section of our presentation focuses on HarmonyOS API usage extraction, often referred to as HAUE. With HAUE's assistance, we can recognize all APIs invoked within the app under detection, subsequently extracting the APIs that applies our detection criteria. HAUE is structured around 3 key components. First, load additional code. At this structure, we integrated all code from DEX files into our system. The second, establish a conditional call graph. This paragraph is crucial as it discerns developers' intended API protections, significantly reducing false positives. The third, resolve API usage. Here, we output the actual runtime versions of API sourced from the conditional call graph, feeding them to HACA. The third section addresses the HarmonyOS API compatibility analysis, abbreviated as HACA. Upon receiving results from both HALM and HAUE, HACA extracts the specific versions of each API as they were added and then removed from the SDK. This data is then mapped to the developer-defined compiler and target versions. and APIs with versions added before the compile and removed prior to the target are flagged as compatibility concerns. That's the whole of our approach section. To verify the effectiveness of our tool, we crafted 3 research questions. However, before diving into them, a credible dataset is prominent. We opted to source HarmonyOS open source projects from Git and GitHub and commercial HarmonyOS projects from App Gallery. The criteria of our selection were clear-cut. The project's primary programming language should be Java. Its API version should range between 4 to 7, and these projects should be compilable and executable. Adhering to these criteria, we culled 501 open source projects and 23 commercial projects, which form the bedrock of our experiment dataset. The first research question we addressed was, can CiD4HMOS effectively detect API compatibility issues within HarmonyOS apps? To answer this, we applied CiD4HMOS across all the open source apps we have gathered. Overall, our analysis uncovered 325 compatibility issues, including 15 forward compatibility issues, distributed across 47 out of the 501 open source projects. Excluding recurring API compatibility issues, we observed 62 backward compatibility issues and 2 forward compatibility issues. Table 2 shows the results of open source projects detected by CiD4HMOS. Our findings were affirmative. CiD4HMOS can have proven to be efficient at identifying API compatibility issues in HarmonyOS projects. With the aid of CiD4HMOS, we can quickly and accurately pinpoint the APIs with compatibility issues. The second research question we addressed was, what types of compatibility issues exist within the current HarmonyOS apps? Are there generic fixes for different types of software compatibility issues? To tackle this, we analyzed the output from research question 1, comparing it against the original program to discern the types of compatibility issues. These were subsequently categorized into backward and forward compatibility issues. We present a classification of existing compatibility issues with HarmonyOS apps and outline corresponding mitigation based on our analysis and examples. The third research question we addressed was, can CiD4HMOS perform practically on commercially released HarmonyOS apps? What has been the feedback from developers on our detection reports? For this research question, we developed CiD4HMOS on commercial applications and relayed the generated output to the developers of apps that exhibited compatibility issues. We reached out to 30 developers in total. We received 8 affirmative responses, whereas 20 developers either did not reply or informed us that their projects were no longer maintained. 2 developers acknowledged our findings but did not take steps to address the identified issues. We demonstrated that CiD4HMOS can provide accurate and permanent information about compatibility issues to developers, enabling them to locate and address these issues effectively. Finally, we have a conclusion to our work. We provide an overview of HarmonyOS API evolution. Our innovative approach, CiD4HMOS, can effectively detect compatibility issues in HarmonyOS apps. Our detailed analysis of HarmonyOS app compatibility issues yield constructive solutions, and sharing these insights with developers gained positive feedback. Thank you for your listening. That's all of my presentation.